This is TWiT.
From Zoom Communications, we have Josh Blum, Simon Booth, Oded Gall, Maxwell Crone, Karen Lyons, Antonio Marcedin, Mike Maxim, Mary Ember Mao, Jack O'Connor, and Miles Steele.
A couple of those names we know well because they came from Keybase.
Ah, exactly.
Yep.
Exactly. And there is a reference to them in the doc. From Johns Hopkins, we have well-known cryptographer and professor Matthew Green.
Wow. Okay.
From Stanford University, we have Alex Stamos.
Okay.
And we also have privacy expert Leah Kistner, formerly Google's global lead for privacy technology.
Pretty impressive.
Their names adorn the top of the 25-page detailed technical cryptography paper they collectively published on GitHub Friday before last on May 20th. That paper is simply titled E2E Encryption for Zoom Meetings, and it begins by stating its purpose. Hundreds of millions of participants join Zoom meetings each day. They use Zoom to learn among classmates scattered by recent events, to collect with friends and family, to collaborate with colleagues, and in some cases, to discuss critical matters of state. Zoom users deserve excellent security guarantees, and Zoom is working to provide these protections in a transparent and peer-reviewed process. This document, mindful of practical constraints, proposes major security and privacy upgrades for Zoom. We're at the beginning of a process of consultation with multiple stakeholders, including clients, cryptography experts, and civil society. As we receive feedback, we will update this document to reflect changes in roadmap and cryptographic design. So, as we've observed here on this podcast, many times across a great many different security challenges, in the end, the weakest link in an end-to-end encryption system is the management of that system's keys. It all comes down to the keys. The task of actually encrypting and decrypting data at each end, given a shared key, has long ago been solved. How often are we talking about the way Apple manages iMessage's keys, and how much does our U.S. Attorney General lust for some form of magical golden key? That's what he wants. So Zoom's security team has properly determined that the first problem to solve, the first place to tighten things, is with the system's key management. Once you have that, then the next weak link is identity, verifying that meeting participant identities are not being spoofed or forged. But it makes no sense to worry about that before you know that the resulting keys are safe. So here's how Zoom describes the operation of their current system, the one they have now. They said Zoom meetings currently use encryption to protect identity, data for meeting setup, and meeting contents. Zoom provides software for desktop and mobile operating systems and embeds software in Zoom Room devices. In this document, when we refer to Zoom clients, we include all of these various forms of packaging. Crucially, these are systems to which we can deploy cryptographic software. Zoom Meetings also supports web browsers through a combination of WebRTC and custom code. If enabled, Zoom Meetings support the use of clients not controlled by Zoom, namely phones using the public switched telephone network, the acronym, or the abbreviation PSTN, and room systems supporting SIP and H323, IP phones technology. They said in the meeting settings, as opposed to webinars, Zoom supports up to 1,000 simultaneous users. Webinars, I didn't realize, Leo, they can be 50,000 people in a webinar.
Yeah.
Whew. When a Zoom client gains entry to a Zoom meeting, it receives a 6-bit per meeting key created by Zoom's servers, which retain the key to distribute to participants as they join. In the version of Zoom's meeting encryption protocol set for release on May 30th, so that has already happened. That was, last Saturday, 3-4 days ago. This per meeting key is used to derive a per stream key. Okay, so essentially what they originally had when we first started talking about Zoom, when coronavirus hadn't yet happened, was a single key which the server created, which was simply distributed to all the clients who joined in order to use that for encryption and decryption. So yes, it was encrypted. Technically, it was end-to-end, but practically the server made the key. So it was no mystery to anybody within the Zoom infrastructure. One of the things that is clearly necessary is to arrange to blind Zoom's infrastructure to the key being used by the clients to communicate, so that the infrastructure is simply transiting pre-encrypted data that it is unable to see into. But they made an interim change on Saturday, May 30th. The per meeting key, which used to just be one, is now being used to derive a per stream key by combining the per meeting key with a non-secret stream ID using an HMAC. Each stream key is used to encrypt audio-video UDP bits using now AES in GCM mode. Remember, they were using electronic codebook, which is not very secure, or at least it leaks information about the plain text, so GCM is way stronger. With each client emitting one or more uniquely identified streams, those packets are relayed and multiplexed via one or more multimedia routers. They call them MMRs, multimedia routers, within Zoom's infrastructure. The MMR servers do not decrypt these packets to route them. There's no mechanism to rekey a meeting. Video conferencing systems in which the server relies on plain text access to the meeting content to perform operations, such as multiplexing, would be exceptionally difficult to secure end-to-end. You're asking for something that isn't end-to-end. In this design, we take advantage of the fact that the Zoom servers do not require any access to meeting content, allowing end-to-end security at exceptionally large scale. And they put in some caveats, of course. If telephones or IP phone clients are authorized to join, in that case, the MMR, the multimedia router, provides the per meeting encryption key to specialized connection servers within Zoom's infrastructure. These servers act as a proxy. They decrypt and composite the meeting content streams in the same manner as a Zoom client, and then re-encode the content in a manner appropriate for the connecting client. Zoom's optional cloud recording feature works similarly, recording the decrypted streams and hosting the resulting file in Zoom Cloud for the user to access. In the current design, Zoom's infrastructure brokers access to the meeting key. So anyway, they're basically saying if you have a client that is unable to have the capability of doing the encryption decryption, if it's a dumb client like a telephone or an IP phone that all it can do is receive and transmit standard data, then they will proxy for that client, and then the link to the client is unencrypted because the client doesn't support encryption. They finish. This current design provides confidentiality and authenticity for all Zoom data streams, but it does not provide true end-to-end encryption as understood by security experts due to the lack of end-to-end key management. In the current implementation, a passive adversary who can monitor Zoom's server infrastructure and who has access to the memory of the relevant Zoom servers may be able to defeat encryption. The adversary can observe the shared meeting key, derive session keys, and decrypt all meeting data. Again, you got to be at Zoom to do that, but still. Zoom's current setup, as well as virtually every other cloud product, relies on securing that infrastructure in order to achieve overall security. End-to-end encryption, using keys at the endpoints only, allows us to reduce reliance on the security of Zoom's infrastructure. And that's where they will be heading. So they divided the task of getting from where they are now to where they want to go into 4 successive phases. And this 25-page document, I saw you had the top of it, Leo. If you scroll down about not that far, like a third of the way, you start hitting all the crypto equations, and it's like, woo, okay. So I mean, it's all there, but it's really not necessary. I mean, essentially, we know how to do crypto now. There's no way for me to discuss the detailed design of the various algorithms on an audio podcast, and there's a large amount of it. But that doesn't really matter, because when it's done correctly, it works. And everybody who's there knows how to do it correctly. The overall architecture is the key, and that can be usefully characterized. So the 4 phases are client key management, identity, a transparency tree, and real-time security. The transparency tree is what the Keybase guys brought to the party, as we'll see in a second. So let's look at what they've explained about each of those briefly. The first phase, they said, in the first phase, we will roll out public key management, where every Zoom application generates and manages its own long-lived public-private key pair. Those private keys are known only to the client. From here, we will upgrade session key negotiation so that the clients can generate and exchange session keys without needing to trust the server. And we know we've talked often about how that's done. Diffie-Hellman key agreement, where in total view, you're able to look at data going in each direction, allows the endpoints to arrive at a mutually known key, but nobody looking at the data going back and forth is able to derive anything of use. So that we're able to do. They'll be adding that in this first phase. They said in this phase, a malicious party could still inject an unwanted public key into the exchange. So that's a good point, that this is not that because authentication is still weak, there is the authentication is phase 2, identity. So as we know, public key crypto allows it assumes you're exchanging with the right person. If a man in the middle does a double exchange with each endpoint, then they don't know that they haven't exchanged with the endpoints themselves. They've exchanged with the man in the middle, who now is able to essentially negotiate separate keys with each of them and is able to form a bridge through which to decrypt in the middle. So they're taking this step at a time, strengthening the infrastructure as they go. They said, we offer meeting security codes as an advanced feature, and we've talked about this too in the past. So motivated users can verify these public keys. The security to be achieved here will approximate those of Apple's FaceTime and iMessage products. We talked about this, I think both Threema and there have been a number of messaging systems where you're able to, over the channel, you're able to say, I'm going to, let's verify like our fingerprints. And so each of the endpoints is able to verify the fingerprint, which cuts out, or at least would immediately alert to any man in the middle. At the moment, that's a manual process. Thus, they said motivated users. they'll be making it automatic. So they said the primary improvement in phase 1 is that a server adversary must now become active rather than passive to break the protocol. In phase 1, we will support native Zoom clients and Zoom rooms. We will not support web browsers, dial-in phones, and other legacy devices. There also will be no support for join before host, cloud recording, and some other Zoom features. Anyway, so I had a note here. I said, so phase 1 takes them from the current encrypted system where the individual client encryption keys could be captured by a passive observer at the Zoom server to a system where Diffie-Hellman secure key establishment is used to blind a passive observer to the client's session keys. Phase 2, identity. They wrote, in the first phase, clients trust Zoom to accurately map usernames to public keys. And of course, you're also trusting that there's no active attacker. They said a malicious Zoom server, in theory, has the ability to swap mappings on the fly to trick participants into entering a meeting with imposters. In phase 2, we will introduce 2 parallel mechanisms for users to track each other's identities without trusting Zoom servers. For users authenticating to Zoom via single sign-on, we will allow the single sign-on identity provider to sign a binding of a Zoom public key to a single sign-on identity and to plumb this identity through to the UI. Unless the single sign-on or the identity provider has a flaw, Zoom cannot fake this identity. So in other words, that's saying that if the UI will be able to attest to the identity of the person on the other end by verifying the signature of the other user's single sign-on identity provider in order to say, yep, there's no way this isn't the right guy, at least as far as single sign-on goes. Or, second, we allow users to track contacts' keys across meetings. That is, the key should be static over time because it's created once in the client. They said this way, the UI can surface warnings if a user joins a meeting with a new public key. And again, we've seen, for example, Signal you can turn on an alert to be alerted if the user's key ever changes. It's like, okay, that shouldn't happen. That could be an active attack. So this tightens up security in a way similar to other, semi-identity managed messaging systems, like I mentioned, Signal and Threema, by remembering previous keys and letting you know if they've changed. Phase 3, a transparency tree. They say in the third phase, we will implement a mechanism that forces Zoom servers and single sign-on providers to sign and immutably store any keys that Zoom claims belong to a specific user. Basically, Zoom becomes a clearinghouse, forcing Zoom to provide a consistent reply to all clients about these claims. In other words, in phase 2, it was up to the user to verify the key of the other end. Now, Zoom is going to be involved in that. It will maintain, very much like a certificate transparency log, it will maintain a log of all the keys of all the clients. That is the public keys, not the private keys, and proactively take measures. They said each client will periodically audit the keys that are being advertised for their own account and surface new additions to the user. That is, if something new appears for their account, it's like, wait a minute, somebody is impersonating you. Additionally, auditor systems can routinely verify and sound the alarm on any inconsistencies within their purview. In this scenario, if Zoom were to lie about Alice's keys, say in order to join a meeting with which Alice is invited to, it would have to lie to everyone in a detectable way. They wrote, we will obtain these guarantees by building a transparency tree similar to those used in certificate transparency and Keybase. During this phase, we will also provide the capability for meeting leaders to upgrade a meeting to end-to-end encrypted after it has begun, provided that all attendees are using the necessary client versions and incompatible features are not in use. Such incompatible features include dial-in phones, IP phone, room systems, and cloud recordings. Meetings that cannot be upgraded will have the option grayed out. We will also re-enable join before host mode, allowing people to show up before the host logs in. And finally, phase 4, real-time security. Consider this hypothetical attack against the phase 3 design. A malicious Zoom server introduces a new ghost device for Bob. A user who does not have their identity provider vouch for their identity. I timed that wrong. A new ghost device for Bob, who is a user, Bob is a user who does not have their identity provider vouching for their identity. Thus, some of the protections that would be available otherwise are not present. The attacker, using this fake new device, starts a meeting with Alice. Alice sees a new device for Bob, but does not check the key's fingerprint. After the fact, Bob can catch the server's malfeasance, but only after the attacker tricked Alice into divulging important information. The transparency tree encourages a trust but verify stance, where intrusions cannot be covered up. In phase 4, we look to the future, where Bob should sign new devices with existing devices, using a single sign-on identity provider to reinforce device additions or delegate it to his local IT manager. Until one of those conditions is met, Alice will look askance at Bob's new devices. In other words, if a new unsigned device, one that has not been signed by an existing trusted device, is used, the UI that Alice is seeing will be saying, look, the Bob, in quotes, is not like following the rules here. We're making no allegations to or attestations that this is actually Bob. You be careful what you say, because it may not be, and you got to have Bob explain why he's using a device that is, that another one of his devices hasn't permitted and authorized and signed. So they conclude saying, across these next 4 phases of security architecture design, we will end up with a state-of-the-art multi-party teleconferencing system which provides robust guarantees of participant identity, takes all key awareness away from the Zoom infrastructure, and is able to proactively alert any Zoom user when something looks wrong. And one thing I noted that I did want to point out about the crypto details was this paragraph. They said, in an ideal world, all public key cryptographic operations could happen via Diffie-Hellman over curve 25519, my favorite chosen curve, and ED-DSA, that's Edwards DSA, over the Edwards 25519 curve, which of course are the technologies I chose for Squirrel, 7 years ago, 8 years ago. Relative to the others, they're writing now, they're saying, relative to others, this curve and algorithm family have shown a consistent track record for resilience to common cryptographic attacks and implementation mistakes. These algorithms are currently in review for FIPS certification, but unfortunately are not yet approved. Therefore, in some cases, like government uses that require FIPS certification, we must fall back to FIPS-approved algorithms like ECDSA and elliptic curve Diffie-Hellman over the P384 curve. These protocols we use have support for both algorithm families. And for now, double up all public key operations to eliminate error-prone if-then-else branching. Once certification succeeds, we can safely no-op the operations over P384 curve. And I thought, what a clever solution. What they're saying there is that since the operations that are where these are being used are inherently not time sensitive, they're one-time setup things, and they're only being used to establish keys and identities, why not use both the 255.19 and P384 curves in series? Then, once 255.19 has been shown to be sufficient, simply drop the P384 out of the chain by no-opping it, and you're left with the curve that you trust. You don't need to worry about implementation mistakes in P384 mucking up the whole crypto. So, nice piece of engineering. I think what they're doing makes total sense, and it's clear to any observer that Zoom is absolutely serious about offering users continuing the same ease of use, but incrementally taking increasing responsibility for making the system much more bulletproof behind the scenes. End users won't notice any difference. It will continue to operate just as it did before, but they will be notified when anything screwy might be happening. So hats off to these guys and to this team that has put this together.
Did they give a ETA for when this will be implemented?
There's no timing at all.
This is just a proposal then.
Yep.
Yeah. But of course, you got the best crypto guys in the world there, so I'm sure it's all well thought out and very sound.
And they don't have to invent anything. All of this is just, applying well-known crypto to solve the particular problem that they have.
I mean, I thought I could see if it's a one-to-one call, that's trivial. That's like messaging. That's like Signal. But I thought it was difficult to do a one-to-many call or many-to-many call because you had to, at the server point, decrypt, right?
I'm stunned, Leo. Yeah. Maybe that's why they specifically said not for webinars, but for meetings up to 1,000. You're talking about a 1,000-way encryption because you've got to encrypt every key pair to every other user. It's like, yo-ho.
And so there's no point at the control point. There's no need for the control point to have a decrypted version. They can route it all based on the crypto keys, and that's all they really need, right? Yeah.
Right.
Yeah, that makes sense. It's just a lot of keys. It's a lot of management.
Well, it's a lot of streams. It's not one stream going up to headquarters and then being sent back out.
Oh, that's a good point. Yeah.
It is 1,000 streams from every user, or 999 from every user to all other 999.
I don't know if that's how they do it normally anyway, or if they try to save bandwidth by aggregating and doing broadcasts.
I think it's the way they've been doing it, interestingly, because they have done end-to-end, but it was just with keys that the server could know about.
Right. Well, and that's what I thought, is that the server needed to know about it to do the routing, but I guess not.
Yeah.
Yeah. Really
well, the good news is symmetric crypto is what you're using with the key.
Right.
And symmetric crypto is fast.
Yeah.
So
it's a lot easier.
Using AES GCM doesn't slow it down at all. So it's all and now Intel chips have AES acceleration in them. They actually have 3 or 4 instructions that like make the most time intensive bit twiddling bit just instant.
That's cool.
So
that's really cool.
Yeah, very.